There we go. So last week, we have finally seen how to properly quantize a relativistic system, the electromagnetic field equations. And how did we do this? Well, we figured out that if we properly write the solutions to the Maxwell equations in terms of Fourier components, then really the coefficients, they contain all the degrees of freedom, and they nicely pair up into these harmonic oscillators. And as soon as we have an infinite set of independent harmonic oscillators, well, we know how to quantize. And this is what we did last week. So what was the result of this? Well, the result was that we constructed this Fock space, or we just used the Fock space that you constructed in the first half of this course. So we stipulate the existence of a photon vacuum state where there are really no photons present. And then for each wave vector k and polarization lambda, we have a creation operator that just adds a photon to this particular state. And you can have any number of these photons per wave vector, and just labeling these numbers for each of these states, it gives us a basis of the Fock space of the photons in this periodic box that we were looking at. Right, so let's summarize a bit. So we have here a creation operator, and sometimes it's useful not to look at the creation operators for the two different polarizations, but to look at the creation operators for the different helicities that a photon can have. So these are particular linear combinations of the two polarizations, which has an imaginary unit in front of one of them, and depending on the relative sign between these two creation operators, it will produce a photon that is either circularly polarized in a clockwise fashion or in anti-clockwise fashion. So this operator, it creates a photon with, let's recall, a momentum h bar k, energy h bar omega k, and what was omega k again? Since these are massless particles, it's just proportional to the magnitude of the momentum, so h bar ck. And as I said, in this particular basis, these are the helicity eigenstates plus, okay, let me use the same color coding as I did there. So for the right-handed version, I get plus h bar, and for the left-handed version, I get a minus h bar. Now, what was helicity again? Helicity, that was the spin of the particle in the direction of its motion. So spin in direction of motion. Okay. And what did you do in the exercises? Well, you verified that this relativistic wave equation satisfies the relativistic principle if the vector potential transforms as if it were a contravariant vector field. And this means that the particles that they're describing are spin 1, spin 1 really meaning that it transforms as a vector, so you have to really rotate the field by a full 2 pi angle in order to bring it back to the identity. Now there is a bit of tension here, because if you recall from, I guess, Quantum Mechanics 1, what were these spin 1 particles? But they were particles or spin 1 wave functions that could take 3 different values for the spin operators, right? So let's do a quick poll here. So there we saw that the spin eigenvalues, say in the z direction or the x direction or the y direction, would always take eigenvalues minus h bar, 0, or h bar. And now we see that if we look in the direction of motion of this photon, then it can only take the plus h bar and the minus h bar. So why is this? Okay, let's see. Yes, so we seem to be converging on the first 2 answers. I agree. The first 2 answers are both correct and closely related to each other. The last answer, I wouldn't say this is really to the point. There is no fundamental difference between spin in non-relativistic systems and relativistic systems, because both they are about how your particle rotates. So really, what's the simplest explanation here? Why can we only have 2 helicity states? Well, because we noticed that there are only 2 local degrees of freedom in the electromagnetic field, right? So there cannot be more than 2 of these states. And why were there only 2 of them? Well, because we had this gauge symmetry. The gauge symmetry allowed us to impose gauge conditions, and we looked at a particular case of the Coulomb gauge, which allowed us to set the scalar potential to 0, and also the divergence of the vector potential. And we used this divergence of the vector potential equal to 0 to eliminate the 0 helicity state. Or to put it differently, if any contribution in the direction of 0 helicity, you can gauge it away, because it corresponds to the polarization being directed in the direction of motion. Okay, so even though this is a spin 1 particle, which usually you would think of as a particle that has 3 internal states, because it's a massless particle, the equations of motion actually admit a gauge symmetry. I could also look at a relativistic wave equation with a mass, but then you would notice that there is no such gauge symmetry. Another way to think of this is, well, how can it be possible that we can forbid the 0 helicity state here? Because clearly this somehow depends on our reference frame, because we're looking at the spin in the direction of motion. If this were a massive particle, we could say, well, let's go to the rest frame of this particle, and there would be no direction of motion. So then there would not be a reference frame invariant way of saying that in the direction of motion we cannot have 0 spin. So that's another way of thinking about this. So let me just write this down. So the 0 helicity state is absent due to the gauge symmetry in the vector potential of electromagnetism. Okay. Are there any further questions about last week's material? Otherwise, we'll continue and draw some conclusions about the quantum statistics of photons. And the first thing I want to look at is the energy of multi-particle photon states. Well, okay, we know this, and you have calculated it in the exercise class as well. So let's recall the answer. So if I have the Hamilton operator acting on one of these basis states in the Fock space, and then what is its energy eigenvalue? Well, we saw that we had a sum over the different wave vectors, a sum of the polarizations, h bar omega k. So essentially the Hamiltonian of a quantum harmonic oscillator with frequency omega k. So we have there the number of quanta plus 1/2 acting in the state. And clearly this is an eigenstate of this operator with eigenvalue just the number of quanta in this particular harmonic oscillator. So that means that, well, okay, of course, this is an infinite energy. Fair enough. But it also means that the vacuum state still has an energy, right? If I apply this to the photon vacuum, I get that it has a 0-point energy, E0. So this is called the 0-point energy, equal to sum over the wave vectors of 1/2 h bar omega k. But they also have a sum over the two polarizations, so that cancels the 1/2. So I simply get a sum over h bar omega k. So even without any photons in the system, I still get this infinite energy. So we should figure out what to make of this. Is this a failure, or can we still continue? So let's start with another poll. So we have this very, very large or even infinite 0-point energy. So is that a problem? Yes, the total energy, it affects the phase of our quantum state according to the Schrödinger equation. Yes, because gravity, or no, because energy differences do not matter. Or can we just harmlessly remove it by slightly adapting our Hamiltonian? Okay, let's see. Yeah, we are settled now. Don't all go to the majority. Yeah, so again, this was a bit of a trick question with no single correct answer. Except the first one, I would certainly say that that is not correct, because I mean, just adding a constant to our Hamiltonian, certainly it is going to change the phase of our state as a function of time, but really this phase is not observable. The second question, or okay, the most obvious answer here is that no, it should not really matter, because energy differences, they are important. They give rise to forces. They are the ones that tell us what happens relatively between two states when they evolve according to the Hamiltonian. But there is one exception here, and that is that the gravity does care about energies, absolute values of energies. Now, for now, we can safely ignore this fact, because we're not going to do anything with gravity at all here, and we don't do anything with gravity in quantum field theory courses to come. But at some point, you should start worrying about this. That if there is a very large energy stored in quantum fields, then somehow it should also gravitate, because general relativity tells us that any form of energy contributes to the curvature of your spacetime. And this is really an ongoing problem, because you can say, well, let's just compensate with some infinite negative energy that cancels this, such that I end up with approximately zero energy. But this is actually very hard to accommodate, certainly in an interacting theory. And then the final answer, that is also a very practical answer, which actually works. So let's look at the two kind of explanations why it's not really a problem. So the first is that in kind of classical physics, and also in quantum physics, as long as we do not regard gravity, then really energy differences are of the essence. So as I said, except perhaps in gravity. And the other remark is that we could have used a slightly different quantization of the Hamiltonian operator here. So we could have made the vacuum state a zero eigen state of the Hamiltonian by choosing what is called a normal ordering. So what does that mean? Well, that means that you look at your operator that we have in terms of the creation and annihilation operators. Which you have shown in the exercise class is really this form. And then we simply say that, well, the better operator, namely the normal ordered one, is the one in which we simply take all the annihilation operators and we put them on the right. So we say, no, you should not have written like this. Instead, we want this also to be of the same form as there. Now, in principle, one is allowed to do this, because the difference is really something that is proportional with h bar. So it's a quantum correction. So the classical harmonic oscillator, it does not force you to use the particular ordering that we used before. So certainly in this case, where we're looking at a free electromagnetic field, we can avoid the 0-point energy by using the slightly different ordering of the operators. Now, this does not solve all problems in quantum field theory, because as soon as you start looking at interactions with other quantum fields, then these interactions can easily turn on again one of these infinite 0-point energies. So one needs a whole theory, it's called renormalization, in order to make sure that these infinite energies do not appear anymore. You'll hear a lot more about this in years to come. Okay. So generally, no, we don't notice the 0-point energy. But there is one exception, if you like. Well, apart from having gravity present. And this is when your box in which you're putting your electromagnetic field is not of a fixed size. So what happens if the dimensions of the box, so remember we looked at a periodic box of side lengths L. What if these side lengths are actually variable? What could be a consequence of the 0-point energy? So let's do a quick poll again. Could it cause spontaneous particle creation? Could it cause an effective temperature for the system, or an effective force, or some modified quantum statistics? Yeah, so what is a 0-point energy? So it's expressed in terms of the sum over the wave vectors. And remember, now k, so it took values in 2 pi over L times the triples of integers. So the values for this wave vector, they certainly depend on the dimensions of the box, right? So the energy, the 0-point energy, will depend on the size of this box. So what happens when you have an energy that depends on a size? Say the energy it increases or decreases when I make the box larger or smaller. Well, that's going to give rise to a force, an effective force, because gradients of energies are forces. So it gives rise to an effective force, and this force is known as the Casimir effect. So when might you be able to observe such an effect? Well, you can imagine a situation where you have two conducting plates, metal plates. So these exclude, or they put the vector potential equal to 0 at the position of the plates. So effectively what they do is they put in a boundary condition for the electromagnetic field in between the plates. So the electromagnetic field, it will have some Fourier modes, but they exactly have to fit in between the two plates. So if you really think of these metal plates as boundaries which separate the electromagnetic field outside from inside, then I could try to calculate the zero-point energy of the quantized electromagnetic field in between and determine from its dependence on the separation a force, in this case an attractive force between the two plates. And this is something you're going to look at in the exercises. Where at least partially you will derive that the zero-point energy is of this form, where A is a separation of the plates and S is kind of the area of the plate. Now you won't be able to do this in mathematical rigor because, as we said, the zero-point energy is actually infinite. So some regularization procedure is needed to be able to compare the zero-point energy between the plates and the region outside of the plates. Okay, so it has long been argued that measuring this Casimir effect, which it was really difficult, but has been done in the 90s, is complete evidence for the existence of zero-point energy. But actually, this is a bit controversial still. And why is that? Well, that's because one is really taking here an idealized situation by thinking of these plates as real boundary conditions on the electromagnetic field. But in reality, of course, these plates, they're constructed from atoms and electrons. And of course, the electromagnetic field does permeate these structures as well. So in the end, any force between these two plates, you should also be able to derive them from just the electromagnetic interaction of these particles in the plate. And in fact, this has been done using calculations in quantum electrodynamics, and they actually reproduce the same attractive force as you calculate from the zero-point energy, without assuming that there is really such a zero-point energy. So what does this mean? This means that, well, it's very useful to think of the existence of zero-point energy to understand the Casimir effect, but that does not necessarily mean that it really exists as a very large energy that is present in the whole space. Okay. So for the remainder of the lecture, I would really like to look at the quantum statistics of photons, and in particular looking at the photon gas. So what do I mean by a photon gas? So this should be some thermal ensemble of photons. So how can I get a thermal ensemble of photons? Well, perhaps I have my box here in which I want to have a photon gas with a certain temperature. Now, how can I give temperature to a photon gas? Well, I need some heat bath, if you like. So Suppose that it really has some physical walls, this enclosure, and these physical walls, they're really in contact with a large reservoir of particles, if you like, at a temperature T. And suppose that the electromagnetic field inside of this enclosure is in thermal equilibrium with this heat bath. Then what does that mean for the distribution of photons inside of this enclosure? So that is a question you would like to answer. So in particular, we want to know something about how many photons are there in the Fourier mode with a particular wave vector k and a particular polarization. So the goal will be to show that the average occupation number is given by the Bose-Einstein statistics Now this we expect because we've seen that photons are spin 1, so they should be bosons. So they should be subject to the quantum statistics of the Bose-Einstein distribution. But in particular with fugacity vanishing. So if you remember from, I guess, the final lecture of Johan, this corresponds to having an average occupation of this state being equal to 1 over e to the beta ek plus alpha minus 1. So that would be in the ground canonical ensemble. But in this case, we put alpha exactly equal to 0. And we want to understand how this particular occupation of the photons inside this enclosure comes about through the interactions that the photon have with the walls of the enclosure. Now, if you recall from also a while back, so this was in fact exercise number 14, you have seen exactly this distribution, and it corresponds to the canonical ensemble okay, let's canonical Maxwell-Boltzmann ensemble. Well, okay, maybe let's not write ensemble. Distribution for the harmonic oscillators involved. So if you forget for the moment that these are particles, that this is a multi-particle system, but just an infinite set of quantum harmonic oscillators, then one can look at the canonical ensemble where or you can put energy in the system or take it out, and then the energy levels, they will be occupied according to the Maxwell-Boltzmann distribution. And it corresponds exactly to this distribution for each individual harmonic oscillator. Okay. But as I said, we would like to derive this from the interaction with the wall. And for this, we have to understand the interaction of the quantized electromagnetic field with a non-relativistic system. Right, so we think of a photon kind of being absorbed by, say, an electron in one of these atoms on the wall, or being emitted by one of these electrons. And we'd like to understand exactly how this process comes about. So if we zoom in on this particular situation, so what does that look like? Well, we can either have an absorption process. So what does that mean? Well, so I have, say, an electron there, which has two energy levels within its atom, if you like. Let's call the corresponding states psi A and psi B. And when a photon comes in, the electron jumps from one level to the other. So suppose this is a photon with a wave vector k, polarization lambda. And okay, we have here a non-relativistic particle of mass m and charge q in order to be able to feel this electromagnetic field. Now we can also look at the reverse process of emission. Where the electron, it jumps to a lower energy eigenstate and then emits a photon. So really this non-relativistic system that we're looking at here is really an electron in the wall of the box. Now, let's make a quick remark here. Let's do a poll for this. There we go. What does this actually mean for the photon gas? The total photon number, is it conserved or not? Okay, yes, I agree. The total photon number is not conserved, right? I have a photon coming in, it kicks the electron to a higher energy level, and then the photon is gone. Okay, you might say, well, perhaps it drops back again and then it emits it, and then we have the same number of photons as we started with. But perhaps this electron will first drop to a different intermediate energy level, emit a photon, and then drop back to its initial level, and again emit a photon. So I went from one photon to two photons. So this is very important for photons compared to, say, a gas of electrons, is in that photon, the total number is not conserved. So note, sorry, photon number is not conserved. So we can always take some, say, thermal energy from our heat bath and turn it into photons. Or vice versa, if I have a number of photons in my gas, I can absorb them in the walls and turn them into thermal energy. And this is also one way to understand why I always have to take the fugacity to be exactly equal to 0. I mean, if you remember in the grand canonical ensemble, how did we derive this ensemble with a variable fugacity? Well, we did this by, or Johann did this by assuming that there is a fixed total number of particles that can migrate from your local system to the reservoir and back. And you minimize the entropy over the different ways that you can distribute these particles in your system and the reservoir. But if the total number of particles is not conserved, then you cannot even do this variational principle. Or to put it differently, if I would take like a positive fugacity, which essentially says that I can add energy or I can lower the energy of the system by putting a new particle in, well, in a photon gas it would be a very unstable situation because I could just add photons from nothing, have them emitted from the boundary, to either increase or decrease your energy as far as you like. So the fact that the gas itself can adjust its number of photons by itself means that we can just put the fugacity equal to 0. Okay, but let's now look in more quantum mechanical detail at these two processes. So how could we do this? Well, we have to write down the Hamiltonian of the combined system of the photons and one of these non-relativistic particles. And we'll just single out one of them. We're not going to model the whole wall. It will be sufficient just to look at a single particle and two of its energy eigenstates. So what will this total Hamiltonian look like? So there will be a Hamiltonian for the electromagnetic field, which we've just seen. So that one depends only on the number operator. Then there will be a Hamiltonian for the particle, which could depend on its position and momentum operators, if you like. Perhaps some internal spin as well, but we'll now only look at the non-spin degrees of freedom. And then there will be some interaction term. So let's denote that by V interaction, which will depend on the vector potential, which is an operator. But it will not just depend on the vector potential at any point, but only at the point where the particle is. So the position of the particle is an operator itself. So we have to put a hat on it. And then it will depend on the position of the particle, if you like, and on the momentum of the particle. But in fact, we've already seen this part of the Hamiltonian. This was exactly the Pauli Hamiltonian in the case of a an electron, a non-relativistic electron. So what does this look like? So we have the standard kinetic term, but we performed a minimal substitution there using the vector potential to get the Hamiltonian of the particle in the electromagnetic field. And to get the full Hamiltonian, we simply have to promote these things to operators. And then we notice that there is also an interaction between the magnetic dipole of the particle and the magnetic field. And in principle, there is also the scalar potential, the Coulomb potential interaction. So after the break, we'll see how to extract the most relevant term from this potential that causes the interaction between the photons and the electron and causes the absorption and emission. Questions here? Okay, let's continue at 4:35. Okay, I'll restart the recording. Okay, so we have the Pauli Hamiltonian. Let's work out the first parenthesis here. So this part, we get a 1/2m momentum squared, so just a standard non-relativistic kinetic term. Then we get a minus q/2m p dot a minus q/2m a dot p and the inner product of the vector potential with itself. Now, okay, so I write these two cross terms separately because in general they do not commute with each other, right? P, this operator corresponds to the derivative with respect to the position, and the position actually appears in the vector potential, as it depends on the position. But luckily, in the gauge that we've chosen, the divergence of A actually vanishes identically. So the term in this part that acts by the derivative on the position of A, it actually vanishes. So really the momentum operator and the vector potential operator do commute. So I can bundle these together. And this is the term that I'm interested in. So let me denote this term by V. Still depends on time, and therefore given by minus q/m. Let me put the vector potential first, dot p, like this. Note also that in the Coulomb gauge, this term is absent. So really the only parts that we're ignoring are a quadratic part in the vector potential. And remember, the vector potential, it had the creation and annihilation operator. So if we take a quadratic part, it will actually produce either two photons or annihilate two photons, while the linear part will only produce one or annihilate one. So it stands to reason that this linear part is actually the dominant one that we will have to look at. And then there is also the interaction between the spin of the particle and the magnetic field that could also cause an interaction. But we're just not going to look at it here. Okay, so we have these operators, and they act on the combined state of both the photons and the particles. So what do they look like? Well, they are a linear combination of pure states, if you like, for the just the one particle, non-relativistic particle. Sorry. And the multi-photon states. Right, because there are these operators. We have the number operators. Well, they only act on the multi-photon states. We have the position and momentum operators. They only act on the particle state. And then in the interaction part, we have both the momentum operator and a position operator acting on the one particle. And well, inside of this vector potential operator, so the field operator, there are still these creation and annihilation operators that act on the multi-photon states. So what we can look at is at two states, let me denote them psi A and psi B, that really correspond to eigenstates of only the particle Hamiltonian. So these are states that satisfy H0. These are energy eigenstates. The particle Hamiltonian. And well, we know that these multi-particle states in the Fock space are also eigenstates of the electromagnetic Hamiltonian. So their combined states are eigenstates of the sum of these, so of the electromagnetic and the particle Hamiltonian. And what we want to do is we want to view this interaction operator as a perturbation. So this v hat of t is a perturbation that can induce a transition between these, well, different of these states, these different eigenstates. That can induce a transition between these. And then we're really in a setting that you should be familiar with quantum mechanics too. You have some base Hamiltonian with a list of eigenstates. So if you were just at this Hamiltonian, then any particle in such a state would remain in this state indefinitely. But then we add a small perturbation to this, and this causes the state to transition to another state at a certain rate. And you can actually calculate this rate at which it transitions. So we're simply going to apply this theory of quantum mechanics 2 to this particular situation. So let's have a bit of a closer look at this perturbation operator V of t. And we can simply fill in, well, what we know about this operator of the vector potential to see what it does. So what did the vector potential operator look like again? So we had a 1 over square root epsilon 0, sum over wave vectors, sum over lambda, h bar over 2 omega k, and then this Fourier component, uk lambda, depending only on the position. And then the Fourier coefficients. Added in this particular way to ensure that the vector potential is real, or that the operator is Hermitian. Now I've forgotten a couple of hats. So now the position has become an operator as well. So this is A, but now I have to take the inner product of A with the momentum operator. So I have an additional inner product P here, and I should put a minus Q over M in front, like this. Now it's actually useful to rewrite this operator slightly by extracting just the time dependence. So let's rewrite this as a sum over k, sum over lambda, then an operator C corresponding to the positive frequency mode. So where is this positive frequency mode here? Well, remember that by definition, this annihilation operator, depending on t, was the time independent annihilation operator times e to the minus I omega kt. So that means that C, what is C here? So we have the minus Q over M. We also have these factors, so H bar over 2 epsilon 0 omega k. There was also a 1 over square root of V in the Fourier component for normalization reasons. So let's also put it there. Then I have the A dagger from here. Yeah, okay, so by convention I am putting a dagger on the C. And the spatial dependence in the Fourier component, simply the Fourier phase, and then I had the polarization for which I take the inner product with P. So if I plug this in here, then I get exactly all the terms for the first one. And then what does the second one look like? I still have the eta lambda there, and then the C without the dagger. And now it's a negative frequency mode. So what are these operators? So they act both on the particle through the position and momentum, but at the same time, this A dagger is producing a photon in the photon part of the state. So what is this perturbation doing? It is at the same time changing your particle eigenstate to a different one with a different energy, as we'll see, coming about because we have this additional phase here. And well, in this particular case, adding a photon. So that should correspond to an emission event, while the C dagger here, which has just an annihilation operator, it destroys a photon and makes a transition between the one particle state to another one. So let me just copy these pictures here for reference. So we're going to apply things that you've learned in quantum mechanics too to this particular perturbation operator. And what we have is Fermi's golden rule. In the setting of periodic perturbation theory, which is just a result of taking the Schrödinger equation for this particular Hamiltonian operator, so H electromagnetic plus H0 plus a very small potential operator, and solving it in the time-dependent Schrödinger equation, starting from an energy eigenstate and ending in another energy eigenstate. Then what you get is a transition rate So what is a transition rate again? That is like the probability of such a transition happening per unit of time, say per second, being related to the matrix elements of the perturbation. Now, which matrix element should we look at? Well, we want to look at a matrix element that is like an absorption and one that is like an emission. So what could this look like? So to get an absorption, we want to destroy a photon. So we have to look at this interaction where I have an A. So that corresponds to the dagger of C. So suppose it acts on an initial state psi A and a photon state with a certain number n k lambda of photons in this particular wave mode. Then, okay, what is the final state I want to look at? Well, if you like, the excited state of this one particle, so psi b. And the only non-vanishing matrix element corresponds to taking the number of photons in this particular wave mode to be one larger. Sorry, one smaller, because I'm doing an absorption. So here I should look at nk lambda minus 1 and compute this matrix element. And what the Fermi's golden rule says is that you have to look at the squared norm of this matrix element And that tells you how fast this transition will happen. But we should also take into account this phase in the perturbation. It tells us that this transition can only happen when the energy of the initial state and the final state differs exactly by the energy that sits in this phase, namely this omega k. So this rate will only be zero if the energy of state B minus the energy of state A is equal to the energy of the photon. But this should sound familiar to you, that you need exactly a photon of the right energy to induce a jump from the electron from this state to that state. And then, okay, there is a 2 pi over h bar in front. Now, similarly, we could look at the emission. So that is it's almost the same formula. I'm cheating a bit here. But now I'm looking not at C dagger, but at C. And what does C do? Well, it creates a photon. So the only non-vanishing matrix element here is if I compare with an end state which has one more photon in this wave mode. And this term comes with the opposite sign phase. So that means that the difference between the final energy of the one particle and the initial one has to be minus the energy of this photon. So that can only happen when really the final energy is smaller than the initial energy. So here also we need a separation of h bar omega k. The particle will jump down and at the same time create a photon, this particular wave vector and polarization. So to know explicitly what these the rates of absorption and emission are, one would of course have to insert some explicit energy eigenstates for this one particle. But now we can already see kind of what the dependence of this emission and absorption is on the electromagnetic field, because that is completely contained in these operators A and A dagger acting on the electromagnetic part of the state. So recall, how does, for instance, the creation operator act on this photon state? Well, of course, it increases it by 1, but we had seen in the construction of the Fock space that there is a normalization factor. Square root of the number of photons before plus 1. So really the square root of the number of photons that you have after you have created this photon. And actually this 1 here is really a purely quantum effect. And it has some repercussions that you would not see if you would just look at this electron interacting with a classical electromagnetic field. So let's make this remark here. If you have many, many photons, so if nk lambda is much larger than 1, then, well, these two states on the left and right hand side, they're pretty much similar. You cannot distinguish them. So really, this creation operator is like multiplying by the square root of n. Also, if n is very large, then there is hardly any difference between the square root of n plus 1 and the square root of n. So that means that emission, because this is the operator that appears in this particular matrix element, is similar to the transition of these energy levels that would happen if you only had like a fixed classical electromagnetic field. And a classical electromagnetic field. So what does it mean to have an electron in a classical electromagnetic field? Well, it's simply saying that you have an interaction now, or a contribution in the Hamiltonian, which has no hat on the vector potential, right? This would just be a fixed quantity. With the classical vector potential being of strength proportional to the square root of n. And then there is the dimensionful prefactor 2 of h bar v epsilon 0 omega k square root nk lambda. So if you have many, many photons in your photon gas, then it is as if you're witnessing a classical electromagnetic field of strength equal the square root of the number of photons that they have in this particular Fourier mode. Now that it's the square root of the number of photons, this should not come as a surprise because well, we said, for instance, that the Hamiltonian of the electromagnetic field, that is expressed as an integral of the square of the vector potential. But the Hamiltonian is linear in the number of photons because every photon contributes the same amount of energy. So this can only be valid if the vector potential really scales with the square root of the number of photons in it. Okay, so that is really the semi-classical regime of the photon gas, where this +1 does not play any role. But one can also look at the situation, which is a pretty common situation, where you have no photons there, so you're in a vacuum. So what happens when I have an electron in vacuum, so no vector potential present at all? Let's do a quick poll. So here really the question is, well, can emission still happen? Both in the classical picture of electromagnetism and in the quantized picture of electromagnetism. What do you think? Or what can you establish based on the formulas that we have here? Okay, so most of you vote for no, nothing can happen in classical electromagnetism, but emission can happen when our electromagnetic field is quantized. I agree. So why is that? So why can nothing happen when you have a classical field? Well, as we said, the only thing that can induce the transition, so the perturbation, for the particle to go from one eigenstate to the other, is through this interaction between the vector potential and the particle. But if the vector potential is exactly equal to 0, then you cannot have a transition because there is no perturbation. So you cannot have an emission or an electron jumping down to a lower energy level if there is no electromagnetic field, classically. But now, in the quantum setting, I have that the creation operator acting on the vacuum state in this particular setting. It is not 0, but it's, well, you get a 1 because of the +1. So this is really the state where I have 1 photon in this particular wave mode. So the interaction operator does not vanish in the quantum setting. It really allows for this electron in vacuum to decay to a lower energy state and emit a single photon. And of course, this happens all the time because most often when we're seeing light coming from our lights or from the sun, then in the particular place where this photon was emitted, there were not many photons present in exactly the energy level of the photon that you're actually observing. So having the electromagnetic field quantized is actually crucial in producing light. And this is a purely quantum phenomenon. So this phenomenon is called spontaneous emission. And it relies crucially on this, the boson statistics in the Fock space. So let's say classically no emission, but in the quantized field we have spontaneous emission. Now in the exercises on Monday, you will use these transition rates to see what it means for the photon gas to be in equilibrium with this particle in the wall. Let me copy this picture. So you will show that if the localized particle, so this electron in its atom, satisfies the Maxwell-Boltzmann statistics, so meaning that its density matrix is distributed over state psi A and psi B according to the standard Boltzmann weights. And it is in equilibrium, so meaning that the transition or the absorption and emission happen equally often. It's in equilibrium with the photon gas. Then this implies that the average number of photons in this state follows the distribution of the Bose-Einstein. with zero fugacity, as we claimed. Okay, very nice. So if we just know the temperature of the enclosure in which we have the photons, then we know exactly, or on average, how many photons there are in each wave mode. So let's look at a couple of consequences there. And the simplest consequence one can think of is asking just what do you see if you then open the enclosure? So what does the photon gas look like? So we have the photons now coming out. What is the energy distribution or the wavelength distribution of these photons? And this is black body radiation. Let's do a quick poll. So if I would look at the total energy of the photons coming out of such a photon gas, how does it scale with the temperature? You remember the law here. And if not, it's fine. We'll actually rederive it in the last couple of minutes. Very good. So we expect it to scale with the temperature to the 4th power. So let's see how this comes about. Well, the only thing really that we have to do is to compute the total energy stored in this photon gas when it's in the equilibrium situation, because that will also tell us how much energy we see coming out when we open the enclosure. So what is the total energy density? So let's denote that by U total. So a density, so we have to divide by the size of the box. And look at the average energy from which we extract the 0-point energy, because that is not going to come out anyway. And we know what to do here. So this is just the eigenvalue of the Hamiltonian. Right? So I have my sum over the wave vectors, sum over the polarizations, h bar omega k, and then the average number of photons in this state. So let us recall this is summing over 2 pi over L times triples of integers. And we want to transform this into a continuum expression. So we want to look, if you like, at the density of states corresponding to this energy distribution. So we turn this sum over k into an integral over k. So we integrate over the length of the wave vector from 0 to infinity. And then, what is the number of such discrete wave vectors in a ball of radius k? So it's 4 pi k squared. So this is first part. Then sum over lambda, that's just going to give you a factor of 2. And here we have a h bar ck, and the Bose-Einstein statistics gives us this e to the beta h bar ck minus 1. And let's change variables from k to the energy E, since E is h bar ck. Then combining all these factors, you have a pi squared h bar to the third, c to the third, e to the third over eta e minus 1. And this is precisely Planck's law. So it tells you that the energy stored in the photons that have energy or wavelength close to E. And it's this very famous curve. Or we can also compute the total energy by actually doing this integral. And what is the answer? Now in terms of the temperature, well, since we have an e to the third here, and e is also integration variable, it scales with e to the fourth, and E is of order the temperature. So we get exactly a temperature to the fourth out. So this is Stefan Boltzmann's law. Okay. Which should be familiar, I think. So really this is Stefan Boltzmann's law for the total energy stored in a photon gas in equilibrium. Usually you think of Stefan Boltzmann's law as the power emitted by a black body. But that is really the same formula, if you like, up to a factor of the speed of light. Because you can imagine if I have here a surface that is emitting black body radiation, then the radiation is traveling with the speed of light, so the amount of energy that you see coming towards you is really the amount of energy that is stored in a cubical container of size, well, the area you're looking at, times the speed of light. So you're really seeing this energy coming towards you.